Okay, so let's come back to the lecture. We don't have too much time left. Then I will discuss with you about the most important thing in lecture 3. All right. So hope you enjoy your quiz 1. Definitely, I think most of you will find some questions or issues when you did your quiz 1, right? So this is something good. I think it's good for me because if you can't find any issues during the lectures, tutorials, or even the quizzes, then you can't remember it quite well. All right. So if you find some issues in quiz 1, then I do believe you will remember about the issues and how to deal with the issues later. So consider it as something good. All right. So because it's only 5%, it's not that much. So consider it as a good thing. And also, I'm going to give you the reflections on quiz 1 after the marks released. And hopefully we can finish it before next Monday. Hopefully, so if we can do that, and definitely I will give a reflection on the quiz 1 during the lecture. All right. So let's come back to the lecture. So again, in this semester, we are not redoing the lecture as what we recorded in the last semester because it's wasting the time. You have everything already, right? So again, it is required that you've watched the videos and also you've have a look at the lecture notes prior to this lecture. Then in the lecture time, we are not go over everything again because it was recorded in last semester and you can see it anytime you want. Then in the lecture time, what we are going to do is we are talking about the most important thing during the lecture, and also we are doing some activities. And if you have some questions, you can bring it to here, then we can discuss together. And the same to the tutorial as well, because for all the tutorials we record the video already, so you can practice, you can watch the video and look at the tutorial materials and practice by yourself. And then Malin will most of time Malin will do the similar things as what I did. So what is the most important thing, and also answer the questions if you have during the practice by yourself. All right. So in the last lecture, we mostly we've introduced the different sensors, and then we concentrate on the camera. The camera means the single camera, then that which is the most commonly used sensor in mechatronics or robotic systems. All right. And the first and the most important thing is we introduced the camera geometry, which is the single wheel geometry, or we call it the camera calibration, which means if you have a 3D point, then how to calculate its projection on the image, right? And you have the question about it in your quiz 1, right? Okay, and then we introduced the calibration. Calibration is also very important as what I mentioned before. So if you if you buy a camera and you want to use that camera in your later project, then some intrinsic parameters, which is fixed, and which means they are constant, and you can use the calibration to pre-calculate it prior when you're using it. Then when you use your camera, for example, when you want to use the camera to do this calculation, then or visual serving or something else, then you can use the intrinsic parameters directly as a constant later, and it really helps a lot. All right, and in the hands-on activities, then we have the camera calibration toolbox, then you tried, and also you have a question on that in quiz 1, in your quiz 1 today, right? And also that is we also include a very simple but useful image processing technique, which is called convolution. So which means if you have an image, you want to extract or enhance some of the information or do some modification on the image, then what you need to do is you just simply modify a kernel function. It can be 3 by 3, 5 by 5, or even larger, and you design that kernel function or kernel matrix. Then you apply that kernel matrix on the image. Then you can do the convolution, and it will process an image from the original one to the one that you may need. For example, edge detection or sharpen or blur, right? And there are some pre-designed kernel matrices, kernel matrices, then you can use if you need this kind of like image processing. All right, so for today we are mainly talking about Rgbd cameras. So in the last lecture, as what we mentioned, in a single camera, you can't recover the depths. You can't recover the depths. But one way you can recover is you move the camera and you cover the depth, but that depth is up to a scale to the real world, right? So in this lecture, we are mainly talking about how can we recover the depth from the single view of the sensors. All right, so we will introduce stereo camera. As I mentioned before, if you use stereo camera, which means every time you can have two images from two cameras at the same time, then you can recover the depth, and also because you know the baseline between them, then you can recover the depth, right? So stereo camera is a way that you can recover the depth from a single view. And another one is, which is much more commonly used at the moment, is the Rgbd cameras. So we will briefly introduce the fundamentals, and also in the hand-on activities, you will previously you can play with the cameras, the real sensors, but in this hand-on activity tutorial, then you will process on some real logged data, and you can find what the data looks like. All right. So for the stereo camera, it is similar to what we have, right? So for the human or most of the animals, we have two eyes. So why we have that is from two eyes we can do the triangulation. Then we know the depth, the distance. So that means why you know an object is far away from you or close to you, right? So it is similar. It is similar for stereo vision. Then today I'm going to show you the techniques or the fundamentals or the methods why we can calculate the depth from a stereo camera. Again, that is very important as well. It is very, very important. All right. So there are some examples. I don't think I'm going to make those in details, but let's go to the most important thing. Before that, let me show you a definition we always used in the stereo, which we called it disparity. So disparity is the pixel difference between two images. Suppose you have two images, and from the two images you can find the pixels with respect to the same 3D point, and the difference of those two pixels, we call it disparity. Then let me ask you a question. So if you have an object which is close to the camera, and you also have an object which is far away from the camera, so which disparity is larger? You can answer the question, unmute yourself, answer the question, or you can put your question in, put your answer in the chat. Think about this question. All right, so I have an answer ready. Yeah, the answer is correct. So, for example, if you have an object quite close to the camera, then which means the disparity. Wait a minute. the disparity is larger, which means the difference between the two pixels from the two images is larger than the one which is a bit far away from the camera, right? What we can get from this, which means from the disparity, we can get the depth of the object or the 3D point, right? So from the disparity, we can get the distance or the depth of the object. And I'm going to show you how we can do that. Intuitively, it's quite easy to understand, right? So as what I wait a minute. Okay, so as what I mentioned before in the lecture 1 and lecture 2, so suppose this is an image and that is a point projection, right? So this is camera center, then we know that point is projected from this ray, right? But we don't know what's the depth, because anytime on this ray, it can project to the same point, right? But suppose we have two images. From both the two images, we can observe the projection of the P from the 3D point, the same point, right? Then we know from the left image, we know the 3D point must lie on this ray. And from the second image, we will know the 3D point is on this ray, right? Right? And which means the intersection between these two rays is the location of the 3D point. And which means we know the location and we know the depth. And this process is what we call triangulation. All right, so this is an intuitive way to let you know why a stereo camera can get the depth comparing to a single camera. But what we can do in the formula point of view, so which means if you have a question, so if you can find two image points from the two images, which is respect to the projected from the same point, how can you calculate the 3D location of that point? How can you really calculate this 3D point location? This is what we call triangulation. And in this is quite important, and I'm going to explain it to you about how to calculate this 3D location by using the method triangulation. All right. So this is, again, is similar to what we have for the single view geometry. So this is an XZ view of the projection, right? And this is the image plane. And this is the first camera. This is the first camera. This is the first camera. Sorry, this is the first camera center. This is the second camera center. All right, and this is the camera axis. This is the camera axis for the right camera. All right. So suppose we have a 3D point P here, and we know the projection relationship, right? So the projection must be on the image plane, but also on the line from the camera center to the 3D point. So which means this point is the projection of point P on the right image, and this point is the projection of the point P on the left camera. All right, so this is an XZ plane, right? So we only consider this plane first, then we are going to see the other one. All right. So in this case, again, we are finding the similar triangles. So if you look at this angle, this triangle is similar to this triangle. Is that right? right? So this triangle is similar to this triangle. Then if we find it out, so this direction is this direction. So this distance is this distance, and which means that distance is the u or x. It's not the u, it's the xl. So which is the x, the location of the projection on the left image. This is the x location of that point, so that projection on the left image. All right. And what is this distance? If you remember, what is this distance? This distance is from the camera center to the image point. So which means that is f, focal length. All right. And what is this distance from P to here, the capital P to here? That is the z coordinate of the 3D point, right? And what is this? What is this distance? What is this distance from CL to this point here? That is the x coordinate. Is that right? That is x coordinate. So from the similar triangles, we can find this distance, the xl divided by f, which is here, is equal to x divided by z, right? So we have this equation already. We have this equation already, right? So only by using the projections on the left image, we have this equation. Then we come back to the projection on the second image, which is here. We can also find the similar triangles. The first triangle is this one, right? This triangle is similar to this triangle. Is that right? So this triangle is similar to this triangle. And again, we have XR, this is XR, right? XR divided by focal length, this is still focal length, divided by F, which is this one here, is equal to this distance. Let me show you here. This distance divided by this distance. All right. So we have this distance, which is Z. But what is this distance? It's quite easy to get because the total distance is x. We've used it already, right? And this distance is the distance between the two camera centers. And what we call it? The distance between the two camera centers, we call it a baseline. We call it baseline, right? So you have that number already. You can do a stereo camera calibration. Then you have the length of the baseline. Then you know the baseline B already. And which means in this, when we considering the projection on the right image, then we have the x minus the baseline B divided by Z is equal to XR divided by F. So now we have one equation from the left image, another equation from the right image. Then, as we can see, we only have the x and z as the parameters unknown. We want to solve them, right? And there's a way how to solve it. So based on the two equations, from the first equation, we can have x is equal to this. And also from the second equation, we can have x is equal to that. Then, which means this is equal to this. Then finally, we have the equation about how to calculate z. How to calculate z? So the z coordinate is equal to the baseline times the focal length divided by XL minus XR. Again, the z-axis is equal to the baseline times the focal length divided by XL minus XR. And what's the XL minus XR? That's the difference of the projections, right? So which means that is the disparity I mentioned before. So which means the baseline times F divided by the disparity is equal to the Z coordinate of the 3D point. All right. Then let's come back. Let's come back to the question I asked you before. So I got the answer that if the point is far away from the camera, then the disparity will be small, right? So in this case, if the disparity is small, then which means the Z is larger, right? So that's the same. And again, from the disparity, you can recover the depth. And if the point is close to you, then which means Z is small, then the disparity is large, right? But if a point is quite far away, then if the disparity is small, then the Z is larger. So this answers the question I asked before. All right. So after you have the Z coordinates of this 3D point, you can put Z into this equation or put that into this equation. Then you can calculate X, right? You can calculate X. But how to calculate Y? For calculating Y is similar as what we have when we think about the single view geometry for the camera. It is the same. So when you consider the YZ plane, it is similar as what you have here. So which means when you have Y, when you are calculating Y, you have a similar equation of this, which means capital Y is equal to Z times YL divided by F. You just simply replace X and capital X and small x by Y, the capital Y and the small y. Then you have similar equation. Then you have Z already. Then you can calculate Y. Then you calculate X, Y, and Z already. All right. All right. So this is about triangulation. So do make sure you know how to calculate it. Do make sure you know how to calculate it. Then let's come back to another question. So here I mentioned XL and XR, but I didn't mention U and V. I didn't mention UL and UR. Can anyone tell me why? This XL and XR are different from the UV value you directly get from the image coordinates. Because if you find here, so this is the camera axis, and this is the principal point, and which means XL means the distance or the coordinate with respect to the origin of the principal point. It's not the origin of the image, right? Which means if you have an UV, you need to first convert that UV with the origin of the principal point as the principal point. And then you can treat it as XL and XR. All right. So let me give an example on the activity 1, but make sure you know how to solve the problem in activity 1, right? So do it by yourself. Definitely do it by yourself. All right. So here there is a principal point of 400 and 300. Then we have the left image point 300, 300. Right image point is 200, 300. Right, and those are the UVs. Not the XL and YL, XR and YR. Then how to convert it into XL and XR, YL and YR? So for example here, the from here we can have the XL, YL, sorry about my writing, I use my mouse to do the writing, is equal to 300 minus the principal point, which is 400 and 300. Then which means when you minus the principal point out from the image UV, then you move the origin of the coordinate to the principal point. All right. Then what you have here is minus 100 and 0. All right. This is very important. I saw a lot of students, they did it wrong. They directly used the UV into this equation, but that is wrong. All right. The XL, XR, YL, and YR, you need to first calculate by doing this. All right. So now the XL is equal to minus 100, and the YL is equal to 0. And similar to XR and YR is equal to, so the UV is 200, 300, again, minus the principal point, which is 400, 300, then which means it is minus 200 and 0. All right. So which means your XR is minus 200 and YR is 0. All right. So you definitely need to do this thing at the beginning and then use the equation I mentioned here. This is very important because I find a lot of students, they make it wrong here. All right. So this is about the triangulation in stereo camera. So that is why you use a stereo camera, then you can get the depth or you can get the location of the 3D point. All right, so now you know the technique, which means you know how to calculate the 3D point from stereo camera, which is the triangulation. You know that already, right? That's quite exciting. Great. So then we move to the Rgbd camera. So stereo can get the depth of the object, but there are some issues with the stereo cameras. The first thing is the color is not consistency between the two cameras. Even they are from the same manufacturing, then they will be different. And this different can make issues when you are extracting the features and matching them. That's a horrible thing. I think I mentioned something before in lecture 1 or lecture 2. And another issue is about the textureless region. Right, so you have some objects, but you need to get the correspondence on the two images. So which means you need to get the object project on image left and image right. You need to do this kind of matching, then you can do the triangulation. But if you are seeing an object with no texture, which means you can't extract the feature and you can't do this kind of triangulation, right? So this is another problem. And also another problem is about the sometimes you can't see the same point from two images, right? So those are some challenges or issues of stereo camera. And also another important thing is sometimes the stereo, if you're using some libraries about stereo recovering to the point cloud of depth, then it's more or less it can get a depth, it can get a dense depth estimation, but it's not that directly. You still need to get the correspondences. Then that is why we have Rgbd cameras. We have Rgbd cameras. And in the camera, you have an RGB image, and you also have a depth image. So which means for each of the pixel, you have an RGB on it, and also you have a depth on it directly. All right. So how does it work? In principle, is about structured light. But currently, some of the newest RGBD cameras, they are using time of flight as well. But generally, they're using structured light. So which means you have a projector, you have IR projector, you have an IR receiver, IR camera, right? So the projector will project some structured pattern, and this pattern will change its shape when the object's shape are different. For example, a very simple example is if you project the parallel lines, then if there's an object on the flat thing, then the line will not be, then the parallel line will not be parallel anymore. So it will change a little bit. All right. So the receiver receives the projection of the from the projector. All right. And then there are some pre-calculations. There are some pre-informations about how to recover the depth from the change of the pattern. Then you have the depth from the camera. All right, so that's the main principle about RGBD camera. But most important thing is how you can use it. You have the camera ready, then you can get RGB and you can get the depth. And how you can use it. So very easy way we are using it is we convert it into a point cloud. Point cloud means it's a collection of points, and also it has some additional features associated to it. And what we always use for the point cloud from the RGBD camera is the RGB. So we give each of the point with an RGB color. So which means if you have an image, if you have an RGB image, if you have a depth image, from the depth image, you can recover the location of each of the pixel, the 3D location of each of the pixel, right? And also, if you give the color from the RGB image to each of the pixel, you can get something on the figure. You can get something on the figure, right? So it's a 3D point cloud together with the color or texture. This is quite useful in the mechatronics or robotic systems. All right, and also I list a lot of different RGBD sensors. Then so they have different features or properties. For example, the distances or the frame rate, and also the size or the resolution of the depth image, and also the RGB image. So which means in your future work, if you need to choose some of the sensors which you can use, which you want to use in your project or something, then those are the things that you can consider. For example, if you want to use the RGBD camera in a very close distance, then you may use this Asus Action Pro sensor instead of the others, because it can work between 0.8 to 3.5. So which, if you want the working distance quite close, you can use that, something like this, which can help you to choose the proper RGBD sensor which you can use in your future. All right, and also, sorry about that. Also, I list a lot of examples about what the RGBD camera can do. I think you can definitely find it from the record I got. I recorded the videos I recorded in the last semester on the UTS Online. All right, so this is all for today's lecture time. Then before we move to the hands-on activities with Marlene, then just one quick thing. I found a lot of students they've joined this Zoom lecture as guests. So which means you didn't log in when you join in. So this is a little bit what the university wants to limit and control. So that's why you need my permission to add you in every time if you are joining in as a guest. So what you can do is you can log in your Zoom app with your UTS account. If you do know how to do that, search on the website about UTS Zoom login. Then you know how to log in with your UTS account. And then after that, after you log in, when you join in this class again, you don't have to wait me to let you in. All right, and this is something that the uni want to control. They don't want anyone to join in to this meeting. So that's why if you didn't log in, then you need my permission to get in. Right, so please log in with your UTS account with your Zoom app. Then you can directly get into this room. All right. All right. So if everything's good, I'll thank you again for joining today's lecture, and then let's move to the HANA activity with Molly. Thank you very much.